So we continue our solution of the second exercise. If you recall, we have solved only part 1. So this is part 2. F is nilpotent if and only if these ring elements AI, where I varies from 0 through n, are themselves nilpotent. And just to recall what F was, this was F. F is this polynomial a0 plus a1x and so on plus an x to the power n, which is an element in this polynomial ring ax, where a of course is the ring, underlying ring from where these elements, these coefficients ai's are coming. So we start the solution first by assuming that these ring elements are nilpotent, and to be more explicit, they are nilpotent in the ring A. But then these polynomials, which are monomials actually, a0, a1x, a2x squared and so on, all the way up to anx to the power n, these are elements in this polynomial ring and they are nilpotent in the polynomial ring. Exactly how that we already saw when we solved part 1. And that is why their sum, which is just our polynomial f, is also nilpotent in Ax. But how? That follows from proposition 1.7. Proposition 1.7 tells us that the nilpotent elements in a ring form an ideal called the nil radical. So if these are nilpotent elements, they belong to the nil radical. So their sum would also be in the nil radical, because the nil radical is an ideal and so is a subgroup of the ring, of this ring under addition. So that's how we have one half of this claim, that if this is true, then that is also true. And next we are going to see the converse. Conversely, let f be nilpotent in Ax. In Ax, that we understand, but it does not hurt to keep writing this, so that at every stage we know where this element belongs. Okay. So f is now nilpotent, that is our hypothesis. And so by part A, 1 plus f, which is this, you just add 1 to f, is a unit in Ax. Actually, I should make it more clear what I mean by part 1 here. By the solution to part 1, where we showed that the sum of a unit and a nilpotent element is a unit, by that result, this is a unit in Ax. But then by the actual statement of part 1, this is also a polynomial, right? And we find that this 1 plus f is a unit. So what does part 1 tell us? It tells us then that 1 plus a0 is a unit and the other coefficients are nilpotent. So we concentrate on the other coefficients, which are just these ai's, a1, a2 up to an. These are nilpotent in A, in the underlying ring A from where they are coming. But then just like the previous part, a1x, a2x squared, all these monomials up to anx to the power n are nilpotent in the polynomial ring Ax. You probably have already guessed what I am going to write next. Hence, a0, which you obtain by removing these other terms in the polynomial f from f, is nilpotent in Ax. Again, by proposition 1.7. Why? Because the fact that f is nilpotent is our hypothesis. That is where this part of the proof starts. And these other elements in Ax are also nilpotent, that we have got here. So this combination should also be nilpotent, because this combination is a combination of elements in the ideal of nilpotent elements, that is the nil radical, because that is closed under this type of combinations. So this thing should be nilpotent in Ax, which is a0. So a0 is nilpotent in Ax. but that just simply means that A0 is also nilpotent in A. Being nilpotent means what? That some power of A0 where the exponent is a positive integer is 0, but A0 originally is from the underlying ring A, so that is why it being nilpotent in AX just simply means that it is also nilpotent as an element of A. So that's how we have got the fact that not only are these coefficients nilpotent, but this A0 is also nilpotent. So that completes part 2. Now let us see part 3 also. Part 3 is about zero divisors in the polynomial ring AX. A polynomial f is a zero divisor if and only if there exists a non-zero element A in the ring A such that AF is equal to 0. By definition, f is a zero divisor if there exists a non-zero polynomial g such that fg is equal to 0. But this exercise, this part tells us that you will be able to find a non-zero ring element so that you multiply f with that ring element, then also you get 0, and by ring element I mean the underlying ring. One half of this double implication is extremely easy, namely that if this is true, then that is also true, and which we have written like this: if there exists a non-zero element A in A such that AF is equal to 0, then obviously f is a zero divisor because this A is after all in the polynomial ring AX as well. It is a constant polynomial. So by definition in this case f is a zero divisor and we are done. And then comes the converse. Conversely, let f be a zero divisor, and now we are speaking an element A like this, so that it is a non-zero ring element in A and such that AF is equal to 0. But the proof will now go by contradiction. What will happen if we suppose that no such A exists? So we make that supposition. Suppose there exists no A in A difference 0 such that AF is equal to 0. But we already have the condition with us. This is our hypothesis that f is a zero divisor. So there will be a g, some polynomial g in AX which is not equal to 0, but such that fg is equal to 0. If we have just that, now there exists a g which say is this polynomial b0 plus b1x and so on up to bmx to the power m, where m is some non-negative integer. In AX difference 0, this g is not the 0 polynomial, but for which such that fg is equal to 0. And again I am saying that we are getting g because f is a zero divisor. Now because such a non-zero g exists, we can also assume that this g has the smallest possible degree m. Note that non-zeroness of g allows us to talk about the degree of g. And there is one more thing to note. Note also that m is a positive integer. How? In general, degree of a polynomial need not be positive, it can be 0 also because there exist constant polynomials. But you look at this supposition, what did we suppose here? We have supposed that there exists no non-zero ring element in A such that if you multiply f with that ring element you will get 0. Now in this situation, under this supposition, if g happens to be of degree 0, then g is just b0, and because g is non-zero, b0 will then be a non-zero ring element, and then this condition will reduce to this, which is something we are not having here under this supposition. So that forces the degree of g, which is m, to be a positive integer. Now next you concentrate on these products, the products of g and the coefficients that we have in f, that is the ai's, where of course I varies from 0 to n. If we assume that all these products are equal to 0, say we assume for a moment that all these products are 0, that means you take any coefficient from the polynomial f and you multiply g with that, you are going to get 0. Then bm times ai will also be equal to 0 for all such I. Why? because this is g. No, multiplying g by ai just simply means multiplying all the terms by ai, because ai is a constant polynomial, and then if that product has to be 0, then all the coefficients must be 0. In particular, ai times bm also has to be equal to 0. But then what is the implication of this situation? The implication is this, but then bm times f is equal to 0. Why? Because if you are multiplying, now if you think of multiplying f by bm, then these will be the coefficients of this product, bm times the coefficients of f. If all of them are 0, then this is automatically 0. But this is the problem. Why? Because it goes against our supposition, which says that we should not find any non-zero ring element in A such that that element times f is equal to 0. Is bm non-zero? Yes, because bm is the leading coefficient of g, and g is by our choice non-zero. So that means this cannot happen, so that is why this also cannot happen. We cannot multiply g with by all the coefficients of f and all of them will be 0. That won't happen. So there has to exist at least one I for which aig is not equal to 0. For the sake of completion, we however write, we do not immediately write this. We write, but this contradicts our supposition. Okay, this thing contradicts our supposition, and that is why aig is not equal to 0 for some I, as we said just now. However, it is very easy to get confused at this point. If we have already got a contradiction, why are we not stopping the proof here? That is because there is still option for us to explore. Do not forget that under our supposition, we came till this point, right? Under that supposition, but then we supposed something new. Okay, this type of nested suppositions sometimes are necessary. So you already have a supposition, you had that, you do not see that here. That supposition, of course, is that fact that, it's not fact, it's our supposition that you cannot multiply f by a non-zero ring element coming from the underlying ring to have the product 0. That was our supposition. Under that supposition, we supposed something else. Although you do not see the word suppose here, but it's also a supposition. That led to something absurd. So that does not simply tell us that the original supposition is wrong. It tells us that this supposition is wrong, and that is why its negation must be true, which is this. Okay. So we now have this. For some I, aig is not equal to 0, because there are only finitely many ai's and hence finitely many i's, because these are the coefficients of f. So there will be such a largest I also. Let j be the largest integer such that j lies in this range between 0 and n inclusive, such that ajg is not equal to 0. Okay. But now what? Now you look at this calculation. We already know that fg is 0, and then I write in the next line what f is. The usual polynomial a0 plus a1x and so on up to anx to the power n. But now I also show this term aj x to the power j, because j can be any index here, it can take any of these values, so this term can be any one of the terms, times g. Now I haven't written one more step, but you can understand that you can apply the distributive law that is there in our polynomial ring ax and multiply all the terms of this polynomial f by the polynomial g, thinking of f itself as a sum of n plus 1 polynomials, and actually it is, right? This is a polynomial, this is another one. So you can apply the right distributive law, its extended version. So that way you will get what? A0g plus A1xg and so on, aj x to the power j times g. Now you look at this condition. Let j be the largest integer such that ajg is not equal to 0. So the terms that will come after this, after you do the multiplication, they will all be 0, because the very next one will be aj plus 1 g x to the power j plus 1, that is 0, the next one is 0 and so on, right. So that is why after doing that and then again taking g common out, this is what you will be left with. Okay, so this polynomial times g is equal to 0. And now you think of the entire product of this polynomial and g. G itself is also a polynomial. In that product, what will be the coefficient of the leading term? That is just the product of the coefficient aj, which is the leading coefficient in this polynomial, and the leading coefficient of g, which is bn. So that product is equal to 0. So this coefficient should also be 0, aj times bn. Alright. Now you will go back to this polynomial ajg. It's a non-zero polynomial, so we can talk about its degree. The degree may be 0, but the degree exists because the polynomial is non-zero. Now after you multiply g with aj, aj gets multiplied with all the coefficients of g, b0, b1 and so on up to bm. But in that bm, that leading term, because aj bm is equal to 0, so that term is not there. The other terms are there, and that is why multiplying g by aj reduces the degree. By how much we don't know, but it is no longer m. We can talk about the degree because the polynomial is non-zero, and at the same time the degree has gone down. It is something less than m, but it's not equal to m. And now we are almost there, we can use this. And now you consider this product f times aj g. I have used square brackets here so that it does not look like we are evaluating the polynomial f at aj g. No, this is just product f times aj g. So it is the product of the two polynomials f and aj g. And of course that is just equal to aj times fg, and fg is 0, so that's how you get 0. But this is the problem. This is a problem because as we saw just now, ajg is a non-zero polynomial and its degree is less than m, and when you multiply f with this, you are getting 0. But that contradicts the minimality of m. Recall what m is. M is the smallest possible degree of a non-zero polynomial, so that if you multiply f with that polynomial, you should get 0. But that itself has been contradicted. And now we have nowhere else to go. We have to now declare that this is a dead end, so our original supposition must be wrong. So we conclude the proof like this. Hence our supposition must be wrong, i.e. there should exist a non-zero element A in the underlying ring such that AF is equal to 0 if F is a zero divisor. After this, of course, we also have another part 4, but its proof is a little long, so we will do it in the next video.